This is the Physics of Extreme Sports, Lab 9. My name is Bridget Savitsky. The problem is that we have a spring that's bobbing up and down and also side to side like a pendulum, and this includes the mass, earth, and spring in the system. We need to find out how this influences the periods of oscillation in the x and y direction and how this influences the energy plots produced. In the main results, we can see that energy is conserved because no work is being done on the system. There's a constant exchange of kinetic and potential energy because of the motion, and also that the period is different for the y and x values. Fundamental principles used in this lab include the momentum principle, where we update velocity and position, and the energy principle, including gravitational and spring potential and kinetic energy. To begin, we know that our system includes the Earth, the spring, and the mass, so there's nothing significant in the surroundings. Initially, we start at rest, but we will eventually have a velocity v. The fundamental principle is energy here. So looking at the code, we had to set some initial conditions, and this includes the position of the ball taken from the tracker data and the initial velocity, which is 0. We had to set the spring constant and find L naught, and then also set what the gravitational potential, spring potential, and kinetic energy would be. This is our time step. And then we had to set the parameters of the graph depending on if it was an energy graph or if it was a position graph. Looking at the while loop to find energy, we noticed the momentum principle in action here in updating velocity, and that the net force includes gravitational and spring force. And finally, we have to update kinetic energy and find the change. Same thing with spring potential and gravitational potential. Total these two potentials, and then the total energy is going to include the potential energy and kinetic energy. In looking at the position code, we are plotting the x and y positions. For the energy plot, the time step had to be very small in order to show the most accurate values for the plots. And when the time step was larger, it actually inaccurately showed how the graphs would behave. When we look at the simulation, you notice that the object doesn't just bob up and down or swing side to side. The combination of the two gives it this complex circular motion. So keep that in mind. Looking at the graph, the red line is the change in kinetic energy, the green is the change in the sum of the potential and of the potentials of the spring potential and the gravitational potential, and then the blue is the total energy. And because we have this circular motion, that means that we've got height changes and we've got compression and stretching, and so that's why we have to look at both the spring potential and the gravitational potential. And so there will be changes in the sum of these potentials depending on the location of the object. And that's why when we look at this graph, the amplitudes on this side are smaller than they are on this side. However, that doesn't mean that energy is dissipating. It's just a difference in the sum of the potentials. And but the energy principle must always be satisfied in that even if the difference in these potentials is approaching 0, or if it's close to 0, there will be an equal and opposite amount of energy that is shifted to the kinetic energy, and we can ultimately see that the total energy must equal 0. So when we look at the of position of the simulation versus the actual values, the red is the ideal spring, which is the simulation, the green is the actual tracker values. This kink is probably due to just how tracker tracked the center of mass. There is, I would say, good agreement between the two, but still not perfect because of sensitivity to initial conditions and chaos in the universe. And the period was ascertained by determining one complete oscillation on this chart. Similarly, this is what the plot of the y values look like. There is not excellent agreement in this graph, but again, I will attribute that to the sensitivity of initial conditions and chaos in the universe. Looking at the period, we have two different frequencies, one in the x direction, one in the y direction. When we look at our measured data and predicted data, we notice that these estimated values of periods are greater, slightly greater in the y direction than they are in the x direction. And I predict that they're different because you have the force of gravity acting in the y direction and not in the x direction. When we look at the energy plots, we can see that there's a constant exchange between potential and kinetic energy, and there's no transfer of energy into or out of the system, and so the energy principle is satisfied. When we look at the equations, we can set work equal to 0, so the initial energy will equal the final. This is what the equation will look like. And we also notice that there's no change in rest energy because the composition is not changing.
And we can easily see that the code and the simulation reflects this principle very well, as the total change in energy is due to the total change in potential energy plus the total change in kinetic energy. So what would happen if we change the origin? I can say the physics of the system wouldn't change. Keep in mind that the energy plots we looked at before are of changes in energy, and because potential is dependent upon the distance between objects with respect to a set origin, it wouldn't affect the plot of the change in gravitational and spring potential. It would look the same, and the same thing goes with kinetic energy. Kinetic energy doesn't change because it's not dependent on distance. It's a property of the system itself. So the plot would look the same.